Well, hello again. It's Todd Booth, and we're on to Network Security Essentials, Chapter 3. But I'm going to do something different. In Chapters 1 and 2, I did just what I call just the facts. And just the facts is just the stuff in the book. Nothing more, nothing less. Try to get through the stuff as fast as I can. I'm going to try something different. I'm going to try in this chapter to do a presentation of the book plus my comments, reflections, and other things. So it's going to be taking a little bit longer, but and then I'm going to ask the students, do you like chapters 2, just the facts, or chapter 3, just the facts plus a little bit more? So let's get into just the facts plus a little bit more. So the title of chapter 3, Public Key Cryptography and Message Authentication. So before we talked about message confidentiality. Message confidentiality means encryption of the message, so even if they see it encrypted, they can't understand it. But there's a lot more to security than that, and we're going to talk about some of those in this chapter. Message authentication is one of those also important network security functions that you need to learn. And we're going to examine different aspects of this message authentication. We're going to look at message authentication codes and hash functions, and they do provide message authentication. And then we're going to look at public key encryption principles and their algorithms. And we can use those in an interesting way. We can use public key algorithms to exchange our previously learned shared key, which is used for symmetric encryption, because we had that problem. How do we move the shared key around safely? And we can use these public key algorithms to do so. And last, we're going to look at public key encryption to produce digital signatures. And they will go ahead and authenticate a message. So what you can do is, well, we all know we can use our printer and print out a page, a letter, you sign it with ink, you put it in the post office, and they look at your signature and they can verify the authenticity of the letter they received. Now we can do the same with computers. I can take a Microsoft Word document or like a PowerPoint, and I can insert my digital signature. And with that digital signature, you can know that it came from me and it hasn't been tampered with. So that's a real world application of this. So let's dig into the details. So we have a couple of quotes here. And encryption provides against passive attacks, eavesdropping. Remember, we want to send it through the wires, but someone may watch the traffic. And even if they watch it, if we encrypt it properly, it doesn't matter because they won't understand the message. So that's encryption. It's a passive attack. They're not trying to change the information. The hackers are trying to just read it and understand it. Now we have a different type of requirement to protect against active attacks. Active attacks, again, are where they try to falsify the data or make it look like it came from someone who it didn't. And an example of that is your grandmother. Your grandmother, and she's using her bank, and she went ahead and typed in her password in her account and sent it in, and she wanted to send her friend €100. But if a hacker is there, they might change the amount from €100 to €1,000. Or they may change it from going to one person for €100 to a different person for €100. They could even try replaying it. So it does send €100, but then they replay the same message again and again and again, and they keep getting transactions of €100 each time they replay it. So we need to stop those, which are called active attacks. A message, file, document, or other collection of data is said to be authentic when it is genuine and comes from its alleged source. You need to know those terms. Now, message authentication is a procedure that allows communicating parties to verify that the received messages are authentic. So the two important aspects are to verify that the contents of the message have not been altered and that the source is authentic. So the source to be authentic, what that means is, for example, you log into your bank, you log into your account, and then you do a transaction. Now the bank wants to make sure that since it's your bank account, they want to make sure that it's actually you at the other end of the internet making the transaction. And that would be the bank wants to make sure that the source, you, are authentic, are who you claim you are. We may wish to verify a message's timeliness because perhaps a hacker will try to delay the message, or perhaps the hacker will replay the message. So if you do a bank transaction and send money to your friend, €100, if your friend intercepts that message and replays it again and again and again, they're going to get €100 again and again and again. That's the replay. We want to prevent that. And of course, they wouldn't be your friend anymore. So we also wish to, in addition to encryption, we talked before, we want to do all of these authentication type activities. And we're going to go into details on those now. Let's talk about the approaches to perform this message authentication. And one way is using conventional encryption, and the other way is to do it without message encryption. So what are the pros and cons here? Well, it would seem possible to perform authentication simply by the use of symmetric encryption. Let's suppose you're sending a message to your friend and you share a key. One of you can use that key to encrypt. One of you can use it to decrypt. You could even put like a timestamp or an error correction code in there. And that would seem to be a solution for message authentication. However, that symmetric encryption alone is not a suitable tool for data authentication. And let's give an example of this. In the ECB mode of encryption, remember every block is encrypted on its own. So you take block 1, 2, and 3, and you'll produce blocks 1, 2, and 3, which correspond to those. When you do the encryption for block 2, it doesn't depend on what happened with the encryption on block 1. And what the hacker can do is rearrange the order of the blocks, and still each block on its own will be decrypted. So that's an example of where encryption alone does not provide message authentication. So what we're going to do now is we're going to talk about different approaches to this message authentication that do not rely on encryption. And even if we could do message authentication with encryption, there are some other ways to do message authentication which are perhaps more efficient and faster and have more features. So what we can do is we don't have to send the message itself encrypted, and we can still on the other side verify the authenticity. So because the approaches we're going to discuss now do not involve encryption, message confidentiality is not provided. But you can always use one approach to solve the message confidentiality, the encryption, and then another approach to do the message integrity and authentication. So we have to find the best way for each different problem we have to solve. We may have one problem to solve, which is how do we do authentication of messages and files on a file system when we have computers read them, and we may have a different problem when we're trying to do a transaction with our bank over the internet. And each problem can be solved in a different way. We have like a toolkit. So in summary, there is a place for authentication and encryption in meeting security requirements. So these are the two of the hot topics in security. Okay, one authentication method involves the use of a secret key to generate a very small block of data known as a message authentication code, a MAC. And we append that to the message. So the MAC could be very small, even though the file could be like a DVD, like 4.5 gigabytes. So this technique assumes that the two communicating parties, for example, you and your friend share a secret key. And when you need to send a message to your friend, then the calculation needs to be performed, which is the function on the key and the message. And the message plus the code are transmitted to the intended recipient, your friend. And when your friend receives the message and the code, they can perform the same calculation on the received message using the same secret key. And they'll generate their own message authentication code, and then they compare the one they generated with the one you sent them. Now, if we assume only you and your friend know the secret key, and if the received code matches the calculated code, then what we think is you would be assured that the message has not been altered, which came from your friend. And if some attacker changes the message but does not alter the code, then you will know it's different, and you'll know it's been tampered with or changed. And because some attacker, they don't know what the secret key is, they won't be able to change the code to correspond with the alterations in the message. So they can change the message, but then you're going to detect it. We also know that the receiver is assured that the message came from the alleged sender. So your friend's going to know it came from you, because no one else knows the secret key, which is shared just between you two. And you can use a whole bunch of different algorithms to generate the code. But the NIST specification recommends the use of DES, data encryption standard, and it can be used to generate an encrypted version of the message. And what we can do is, this is interesting, we just take the last bits of the ciphertext that was generated by DES encryption, and we can use those as the code. And we might want to use 16 or 32 bits. So the process we just described, it's similar to encryption, but it's not exactly the same. For example, the authentication algorithm need not be reversible. So we don't have to save all of the output from DES. We can just save the last 32 bits, for example. And it turns out that the mathematical properties of authentication make it less vulnerable to being broken as compared to encryption. So here's one alternative. Instead of using the encryption, we can use a message authentication code via a one-way hash function. So as with the message authentication code, a hash function accepts a variable size message. It could be 1K, a megabyte, a gig, doesn't matter. And it produces the fixed size small message digest as output. So unlike a Mac, a hash function does not take a secret key. To authenticate a message, the message digest is sent with the message in such a way that the message digest is authentic. So that's interesting. We don't have to use encryption. We can just use another hash function, and then we can generate that digest. And then we just have to find a way to get the digest over there where it can't be tampered with. So in this illustration, we have three ways in which the message can be authenticated. We can go ahead and take the message digest, and then we can encrypt the message digest with conventional encryption. And as usual, if only the sender and receiver shared the key, then we have authenticity of the exchange of the digest. So isn't that interesting? Instead of using encryption, and the output is a message authentication code which is encrypted, we can use just a regular old hash function. It generates a code, and then we take the code output, and then we put that through and encrypt it. So the message digest can be encrypted using public key encryption, and we have some advantages with that. It'll provide a digital signature as well as message authentication. And the digital signature, we can verify the authenticity of the sender. We know who it came from. And it does not require the distribution of keys to communicating parties. And we'll talk about how the public key infrastructure can allow us to do that. So these two approaches have an advantage over the one that encrypt the entire message because it takes less time. Think of it. You've got a message which is, let's say, 4 gig of bytes of data. And if you want to encrypt that to create a MAC, then you've got to do the encryption through the whole thing. But we can use these hash functions, and we're not actually doing encryption. And then the output of that perhaps we'll want to encrypt. So, and then on the left, on the C chart, that shows a technique that uses a hash function but no encryption for message authentication. And because the secret value itself is not sent, it is not possible for an attacker to modify an intercepted message. So we just have to keep that secret secret. And that will prevent an attacker from generating a false message. And there's a variation on the third technique called HMAC, which is also used for IP security. We'll talk about that later. Now, the purpose of the hash function is to produce a fingerprint of a file, message, or other block of data. To be useful, a hash function must have the following properties. It must be able to be applied to a block of data which could be any size, very small or very large. And it has to produce a fixed length output, no matter how big the message is. It should be relatively easy to compute the function, making both hardware and software implementations practical. And as before, with any given code, it should be computationally infeasible for the hacker to try to find the message. And a hash function with this property is referred to as one-way or pre-image resistant. And for any given block X of the message, it should be infeasible to find Y, which would be a different message which has the same output, the same hash function output. And this is sometimes referred to as weak collision resistant. And it should be computationally infeasible to find any pair XY so that the hash of X equals the hash of Y. And that would be collision resistant. It could also be referred to as strong collision resistant. And a hash function that satisfies the first 5 properties would be weak hash function. And that 6th property, if that's also satisfied, it would be a strong hash function. And that 6th property, collision resistance, protects against a sophisticated class of attack, which is known as the birthday attack. So let's talk about the security of this hash function. So we have different approaches. So as with symmetric encryption, there are 2 approaches to attacking a secure hash function: cryptanalysis and brute force attack. So as with symmetric encryption, cryptanalysis of a hash function involves exploiting logical weaknesses in the algorithm. So when they design these algorithms, they try to make them as fabulous as they can, but sometimes when you really analyze things in different ways, you can find some weaknesses, some vulnerabilities, which will give the hacker the edge to try to break the code. So the strength of the hash function against brute force attacks, where they just try every possible number, it depends solely on the length of the hash code produced by the algorithm. So you could have a hash code output which is 1 bit, but brute force, they could just try the bit to have value 0 and 1. So they're going to find that pretty quick. But let's say you have 2 bits. Well, the hash code output could be 00, 01, 10, 11. So that's like 0, 1, 2, 3. And they could just try all those. But let's say you had 16 bits. Then it would be 2 to the 16th, and for brute force they have to try about half of them, which would be 2 to the 15th, and so on and so forth. So you can create these very, very long hash function outputs, and then brute force will have a real tough time because they're going to have to go through about half of the possibilities. So if collision resistance is required, and it often is, then it's the value of 2 to the n/2, which determines the strength of the hash code against a brute force attack. Oh, and I want to mention that 2 to the n divided by 2. I mean, with parentheses 2 to the n, close parentheses, and then take the whole thing, the result of that, divided by 2, which is also 2 to the n minus 1. So someone designed a collision search machine for $10 million, and it was trying to find collisions for MD5. The MD5 has a 128-bit hash length, and the machine could find the collision in 24 days. So a 128-bit code may be viewed as inadequate, so we need to make it longer. So the next step up, if a hash code is treated as a sequence of 32 bits, would be a 160-bit hash length. So that would be the 128 plus 32 equals 160. So with a hash code of 160 bits, the machine would require over 4,000 years to find a collision. And with today's technology, it'd be much shorter. And what do? We can just make the 160 bits longer. So all hash functions operate using the following general principles. We've got the input, which is the message or file, and it's viewed as a sequence of n bit blocks. So the input is processed one block at a time in an iterative fashion to produce an n bit hash function. So one of the simpler ones is a bit by bit exclusive OR, XOR of every block. And in the figure, we can see this operation. It's producing a simple parity for each bit position. Okay, so let's talk about how this hash function works. We have some general principles. So the input is viewed as a sequence of n-bit blocks, and it's processed one block at a time, and it produces an n-bit hash function. And one of the simplest hash functions is simply a bit by bit exclusive OR. And this figure illustrates that. So why don't I give you an example? Let's suppose we're up here in this chart and we're using a hash where the output is 128 bits. We might take as input 1 meg, 1 gig, 10 gigs, doesn't matter. 128-bit is the hash code size. So this would be bit 1, bit 2 of the hash, etc. through bit n would be 128. So we got the bits lined up here. So we divide this big file, let's say it's a gig, and we divide it into blocks. The first block would be how many bits? 128. And the 129th bit would start over here in the second block, and it would go for 128 bits. So we divide the big file up into these blocks. And it doesn't matter how many blocks are. There could be 2 blocks or 2,000 blocks. Okay, so we got the blocks divided up. We got the bits lined up here. And then the hash function can be, for example, an XOR of these bits here. The first bit in each block. You got it? And then the output would be here. Okay, now the second bit of the hash output, that's the digest that we get, is an exclusive OR of the second bit in each of the blocks, etc., so on and so forth. Okay, we've talked about some theoretical technical knowledge, and now we're going to talk a little bit about some practical matters, practical skills. We have an implementation of hash functions called SHA, Secure Hash Function, and it's the most widely used hash function today. Okay, and the reason is because virtually every other widely used hash function has been found to have substantial cryptanalytic weaknesses. So SHA was basically the last remaining standardized hash function by 2005. So SHA was developed by NIST and published as a FIP standard. And when weaknesses were found in SHA, they came up with SHA-1. And the document is called Secure Hash Standard. And because SHA is based on MD4, the design of it closely models MD4. Now, SHA-1 produces a hash value of 128 bits, and that's long enough. But even SHA had some problems. So in 2005, the NIST announced it's going to phase out approval of SHA-1 and move to a reliance on SHA-2 going forward. And isn't this amazing? We have hundreds of thousands or maybe millions of security engineers around the world. And even with that, they've come up again and again and again with these hash algorithms which have vulnerabilities. And they had to move to SHA, and then even SHA has vulnerabilities, and we have to move on to the next version of SHA. It's simply amazing. So that means that this security is not as easy as people would think. So it does take a lot of time to learn this in detail. Okay, well, let's have a comparison. We've got a comparison of different SHA parameters. And across the top, we've got starting with SHA-1. And remember, the first one was SHA. It's not even listed. And we can see as we move to the right, we have an increase in the length of the message digest. So it was in 2002 that NIST defined 3 new versions of SHA, and they have hash values of 256, 384, and 512. And we just called them SHA dash whatever the bit size was. So collectively, altogether, it's known as SHA-2. So SHA-2 has 3 different hash value lengths. And the new versions have the basic underlying structure and modular arithmetic as the SHA-1, which was revised. And SHA-1 and SHA-2 are specified in the request for comment 6234, and it basically duplicates that material, and it has a little bit of a change. So that's the layout. So here's the algorithm. Take a look. So we take as the input a message with a maximum length of less than 2 to the 128 bits. So that's a big message. And it produces an output of 512-bit message digest. And the input again is processed in blocks, in this case 1024. And the picture depicts that the overall processing of a message to produce a digest is done in this form. You can see at the very top we've got the message, L bits, and then we break into blocks. Here's the 1024 bits, that's 2 to the 10th power. There we go. And we process each one separately, and we create the hash values down here. And the hash code, the last bit of the hash code is over here. Hash code bit 1, bit 2, through N. And here we have up here 1024 bits, and each one is based into a block. So we've got a hash code of 1024 bits, again 2 to the 10th. So here's the heart of the algorithm. It's a module that consists of 80 rounds. Again, round, you do some kind of computation and then you put it through the same type of computation again and again and again. That's 80 rounds of computation, and it's labeled over here. We've got case of 0, case of 1, ... case of 79. Quite often we start counting from 0. So 0 to 79 is 80 rounds. Okay, now look at this, SHA-3. So let's talk about SHA-2 first. With SHA-2, and in particular, we got 512 bits we can use, and it would appear to be incredibly great security, 512 bits. Remember, we thought 160 was good to go, and if it isn't, we can make it twice as hard as the hacker by just adding 1 bit, and that would be 160 to 161. And here we are at 512. But the thing is, the SHA-2 shares the same structure and mathematical properties as its predecessors in SHA, and they have the weaknesses. However, the problem is it could take years to find a replacement for SHA-2 in case it becomes vulnerable. And if it becomes vulnerable, what that means is all of the previous messages that the hackers have, they can use those vulnerabilities to try to attack and obtain the plain text of all those messages. So you really want to have some protocols that we can rely on for at least 50 years. And here we are finding vulnerabilities in these hash functions all the time, it appears like. So NIST announced in 2007 a competition to produce the next hash function, which would be called SHA-3. And here are the requirements for SHA-3. It needs to be able to replace SHA-2 in any application with a simple drop-in substitution. So if we have like millions of applications that are coded to work with SHA-2, we want to have the interface of SHA-3 in a very similar manner. So you can just pop out one and pop in the other, and we don't have to do any programming on all of these applications that are out there. And SHA-3 must support hash values of 224, 256, 384, and 512 because they were supported before. And it has to preserve the online nature of SHA-2, meaning that it has to be able to process small blocks in like 512 or 1024 at a time. And it shouldn't have to require, for example, to process the whole message in buffered memory before processing it. So, and it was 2012, so not so long ago, just last year, that the NIST selected a winner, and they formally published the winning algorithm as SHA-3. And that'll be covered later in this book. So HMAC. So in recent years, it's been in an increased interest to develop a MAC derived from a cryptographic hash code, such as SHA-1. So the motivation is the following. The cryptographic hash functions generally execute faster in software than conventional encryption algorithms such as DES. And again, DES is great. They haven't found any vulnerabilities. It's the most studied encryption protocol, but it's not fast. So we also want things that are fast in software and hardware. Also, we have a lot of library code out there so that programmers can easily create cryptographic hash functions. And the hash function SHA-1, it was not designed for use as a MAC, and it can't be used directly for that purpose because it doesn't rely on a secret key. So there have been a bunch of proposals to try to incorporate a secret key into an existing hash algorithm, and there's different ways that have been used. So HMAC design objectives. So we have a bunch of design principles. So you can see to use without modifications, and to make it without modifications allows us to use existing software without making changes, which can be very expensive. So we want to do that without modifications and use available hash functions. And we want hash functions that perform well efficiently in software for which the code is freely and widely available. We don't want to have a big licensing fee to use different solutions here. We'd like it to be freely available. And widely available is not exactly the same as free. Widely available, we want to make sure that there's no restrictions on export. So it may be developed in one country, and we want to make sure that we can export that technology for no cost easily to the whole world. And we want to preserve the original performance of the hash function. So we don't want it to be slower. So we have some challenges. And we want to be able to use the keys in simple ways. Remember we talked about we want to be able to understand the algorithms used in encryption so that we can analyze them and make sure we can't find weaknesses. Same thing here. We want to have a well understood cryptographic analysis of the strengths of the authentication mechanism based on assumptions, and we want to embed those algorithms in the hash function. So The first two objectives are important for acceptability of HMAC. So we want to treat this hash function as a black box. And that will allow us to have existing implementations in a modular implemented way. And the bulk of the code could be prepackaged in these libraries to make it easier for programmers. And then we just reuse it without modification. And if we ever have to replace a given hash function in an HMAC implementation, we want to make it sure that it's so easy for the programmer. We just remove the existing hash function module and we drop in the new module, and then the programs work. And we don't have to have like the next generation of HMAC, which is less vulnerable. Even if we find a faster implementation, which executes more efficiently in hardware and software, we want to be able to replace the old module with the new module and have it work fine with no modifications to the software. And that's why we want to treat it as a black box. And this last design objective is, in fact, the main advantage of HMAC over other proposed hash-based schemes. It can be more secure than the embedded hash function, as long as we have some reasonable cryptographic strengths. And we're going to return to this later, but we need to examine HMAC so you can better understand what it is and how it works. So here's the algorithm on how it works, and it's covered in the book as well. So you can see the cipher-based message authentication code mode of operation, and that's used with AES, and it's also used with TripleDES. So a counter with cipher block chaining message authentication code. And again, cipher block chaining means we process one block and we have some kind of input from that into the next block. And that again is to stop from the attack where all of the blocks are encrypted on their own, because the hacker can rearrange them. So the counter with cipher block chaining message authentication code, CCM, mode of operation, is referred to as an authenticated encryption mode. So the authenticated encryption is a term to describe encryption systems that simultaneously do two things. They provide confidentiality and they also provide authenticity of the communications. So many applications and protocols require both forms of security. But until recently, the two services were normally designed separately. And there are some advantages to design them together in one for just those applications that need both. So the key algorithmic ingredients of this CCM are the AES encryption algorithm and the CTR mode of operation. And then we use the CMAC authentication algorithm. And we're using the same key for both the encryption and the MAC algorithms. So here you can see the operation of the CCM. Now for authentication, the input includes the nonce, the associated data, and plain text, and it's formatted as a sequence of blocks like we've had before, block 0 through block R. And it's the first block that contains the nonce plus some formatting bits that indicate the length of the different elements. And then we have 0 or more blocks that contain A, followed by 0 or more blocks that contain P. And the resulting sequence of blocks serves as input to the CMAC algorithm. And it's going to produce a MAC value with a length of T length, which is less than or equal to the block length. Now, for encryption, a sequence of counters is generated that needs to be independent of the nonce. and the authentication tag is encrypted in the CTR mode using the single counter. And then the TLEN most significant bits of the output are XORed with the tag to produce an encrypted tag. Now the remaining counters are used for the CTR mode encryption of the plaintext. And the encrypted plaintext is concatenated with the encrypted tag to form the ciphertext output. So it gets a little more complicated when we're trying to do both encryption and authentication in the same algorithm as once. But if you can get that done right, then you're going to have some advantages over trying to do the encryption on the one hand and the authentication on the other hand using separate functions. Okay, now we're talking about something quite different. Public key encryption structure. And this is opposed to that symmetric where we have a single shared key. Now, and also this is quite new. So public key encryption, it first publicly was proposed by Diffie-Hellman in 1976. And it's a real revolutionary advance in encryption. For thousands of years, we used the old way, symmetric encryption, a shared secret key. And very recently, again, public key encryption came. And public key algorithms are based on mathematical functions instead of on simple operations on bit patterns, which are used, for example, symmetric encryption. So, and more importantly, public key cryptography is asymmetric, involving the use of two separate keys. And that's in contrast with symmetric shared key. Now, the use of two keys has some really nice consequences in the area of confidentiality, key distribution, and authentication, which is what we've been focusing on. Okay, now you need to understand some things about some common misconceptions concerning public key encryption. And one of them is that it's more secure than conventional symmetric encryption. And that's not true. In fact, the security of any encryption, whether it's public key or conventional, it depends on the length of the key because of the brute force, remember, and the computational work involved in breaking a cipher. We look for vulnerabilities in the algorithms. And there's nothing in principle about either conventional or public key encryption that makes one better than the other. From the point of view of cryptanalysis, the hackers trying to break the codes. And another misconception is that public key encryption is a general purpose technique that has replaced conventional symmetric encryption. And that's not true at all. Symmetric encryption has some advantages over asymmetric public encryption and vice versa. So what we're going to see is we're going to use both for a long, long time. And what we're going to do is use one where it has some advantages and use the other where it has some advantages. And some people have a misconception that key distribution is trivial with regard to public key encryption, when in fact there are some challenges with both public key encryption and with conventional encryption. Okay, now a public key encryption scheme has 6 ingredients. They've got the plaintext, the encryption algorithm, the public and private key. So that's different. Before we had one shared key, now we have a public and a private key. And that would be a pair of keys that have been selected so that if one key is used for encryption, the other can be used for decryption. And the exact transformations performed by the encryption algorithm depend on the public or private key that is provided as input. We still have our ciphertext, which is the output encryption. We have the decryption algorithm, and that's the one that accepts ciphertext in the matching key and produces the original plaintext. Now, the key used in conventional encryption is typically referred to as a secret key. The two keys used for public key encryption are referred to as the public key and the private key. So it's the private key that we need to keep secret. It's referred to as a private key rather than a secret key, so we don't get confused with conventional encryption. So before we go on, we need to clarify some things about public key crypto systems that otherwise might lead you to some confusion. So it's the public key systems that are characterized by the use of a cryptographic type of algorithm with two keys, one held privately and the other one available publicly. And there's different applications that can use this, and it depends on the application if the sender uses either the sender's private key or the receiver's public key, or maybe both, to do the cryptographic functions. So we can classify the use of these keys in three major categories. We have the encryption decryption. And in that situation, the sender encrypts a message with the recipient's public key. We have a digital signature, which we may want. And in that situation, it's the sender who signs the message with their private key. And the signing is achieved by a cryptographic algorithm applied to the message or to a small block of data that's a function of the message. And we have another function called a key exchange. And the two different parties want to cooperate to exchange and create a session key. And the session key can be used for conventional encryption. And there's different approaches we can use involving the private key of one of them or of both of the parties who wish to communicate. Okay, now some algorithms are suitable for all three of those applications, whereas other algorithms can be used for only one or two of these applications. And that's kind of like what we talked about before. We might wish to have integrity of a message, or we may wish to have message confidentiality. And we can use two separate functions, and that's what was done for a long time. But now we can also have one algorithm which does both. And we have the same thing here for the different types of applications for public key encryption. So we can combine the functionality into like one massive function that does more than one type of service, public key service. So here we have a table, and we have different algorithms on the left, and you can see that some of them are used for different features. We have, for example, the RSA algorithm can be used for encryption, decryption, digital certificate, key exchange, for all three. But look, Diffie-Hellman, no encryption, decryption, no digital signature, only for key exchange. So that's what we're talking about. And over here, DSS, we've got no and then a yes for digital signature, and that's all it does. Okay, let's talk about the algorithms. We have public key algorithms. The two most widely used are RSA and Diffie-Hellman, DH. There's others, and we'll look at those later. But one of the first ones for the public key schemes was RSA, and it was published in 1978. And since that time, it's become the most widely accepted and implemented approach for public key encryption. Now, it's a block cipher, and the plain text and ciphertext are considered as integers. So we convert them to integers, convert the plain text and ciphertext, and then we run these mathematical formulas on them. And this figure summarizes the algorithm. And it deals with prime numbers as well as part of its algorithm. So here's an example of the RSA algorithm, and it's doing modular arithmetic. So Diffie-Hellman key exchange, or DH key exchange, it appeared in a paper by Diffie-Hellman, and it is generally referred to as the Diffie-Hellman key exchange because that's its main use. A number of commercial products actually use this. So when you configure, for example, a Cisco VPN server, you can use DH to do the key exchange with the other device. And it's a very popular protocol that's used on most network equipment that implements VPN. Now, the purpose of this algorithm, of the key exchange algorithm, is to enable two users to exchange a secret key securely. And then they're going to use that secret key for a session. Isn't that interesting? They use asymmetric encryption or public key encryption, and then they can use this DH algorithm to exchange a symmetric shared key, and they exchange it. And then for the rest of the session, they can use the symmetric encryption. And you might think, why bother? Why don't we just do the asymmetric encryption the whole time? Well, it's not as fast and efficient, but it is good at exchanging a secret key. So we use the asymmetric, what it's good for, exchanging a secret key. And then we use that key for the session, and we run conventional encryption, the symmetric encryption. So this algorithm is just limited to exchanging of the conventional shared key. So the Diffie-Hellman algorithm depends for its effectiveness on the difficulty of computing discrete logarithms. And that's why it is very powerful. But we still can exchange keys in a secure manner. Very nice. So here we have a summary. I'm not going to go through it all. You can just read through it slowly, what Alice and Bob do. And those are two of our favorite characters in security, Alice and Bob, and they want to communicate. And you can just read through these blocks and see how they can use Diffie-Hellman to exchange a shared key, which they can use for symmetric encryption for the rest of the session. So the protocol we depicted in the previous slide on the last page, it's insecure against a man-in-the-middle attack. And here in this illustration, look, we have this man in the middle, Darth, and Darth is trying to intercept the messages and understand what's going on between Alice and Bob. And look at what Darth does. When Alice tries to communicate with Bob, the man in the middle intercepts that message. And from the point of view of Alice, Darth tries to appear to be Bob. And then at the same time, when Bob tries to communicate with Alice and reply to her messages, which the man in the middle forwards, Darth intercepts those. And then Bob can send the messages to Darth, and then Darth intercepts them, and then Darth sends messages to Alice as if they came from Bob. Now that's a classic man in the middle attack. So the last protocol on the last page doesn't stop that. So there's some problems there that we have to solve. Okay, now we have something called the Digital Signature Standard, DSS. And it's back to the NIST, the National Institute of Standards and Technology from the US, but a lot of countries around the world listen to what they say and follow the same things. And it's one of those FIPS standards, again, the Federal Information Processing from the US. And it's known as the Digital Signature Standard, DSS. And it makes use of our friend SHA-1 and presents a new digital signature technique. It's called the Digital Signature Algorithm, DSA. So the DSS was originally proposed a long time ago, and it was revised in 1993 based on public feedback, and they tried to improve the security, and they had another minor revision in 1996. And it uses an algorithm that's designed to provide only the digital signature function. Remember we talked about you can have like one protocol for encryption and one protocol for authentication, or you can have one protocol, one big one that does both. Well, in this situation, this protocol, the DSS, it's only doing one function, the digital signature function. And unlike RSA, it cannot be used for encryption or key exchange because all it does is the digital signature function. Okay, well, there's something else, another algorithm called elliptic curve cryptology, ECC. So, the vast majority of the products and standards that use public key cryptography for encryption and digital signatures use RSA. And the bit length for secure RSA has increased over the years. And that puts a heavier processing load on applications using RSA because they have to do a lot of computational work to run these algorithms. And what do we want to do? We talked about it before. We want to keep finding newer ways to do things that are faster and more efficient. So when we make the key size larger, it takes a lot more power. So we have to think about how to solve it better. And this RSA is really popular for like electronic commerce sites. So when you're doing exchanges over the internet, you're getting credit cards from customers, etc. RSA is used a lot. But if we make the key really long, we're going to slow down the application on both sides, both on the client side and the web server side. So they came up with this competing system to challenge RSA. It's not that it's necessarily more secure, but they want to do things more efficiently. And it's called elliptic curve cryptography, ECC. And it's showing up in standardization efforts. And the big attraction of ECC compared to RSA is that it offers equal security for a smaller bit size, therefore reducing processing overhead. On the other hand, although the theory of ECC has been around for some time, it is only recently that products have begun to appear and that there have been sustained cryptanalytic interest in probing for weaknesses. So the confidence level in ECC is not as high as RSA. Now, ECC is fundamentally more difficult to explain. We talked about that before. Remember, we said the more difficult it is to explain an algorithm, the more difficult it is to see if there are weaknesses in it. So it may be around for a long time before people find ways to find the vulnerabilities in different algorithms. So that's a minus. And not only is it more difficult than RSA, it's more difficult than DH as well. And a full mathematical description, well, that would be too much for this course, so we're going to skip that. However, the technique is based on the use of a mathematical construct known as elliptic curve. And then we have, at the end as usual, our chapter summary. I'm not going to read through this, but I'll at least hit a few highlights. So we talked about message authentication and then the secure hash function, digital signatures, just like real signatures, but they're for computer applications to sign documents or email. And then we talked about message authentication codes and public key cryptography. Again, that's quite new, and it's not a competitor alone to symmetric conventional encryption, but it has some features that symmetric encryption doesn't have and vice versa. And then we talked about different algorithms which implement the public key cryptography. So thanks for listening, and bye for now.